Well, in this video, we're going to take a look at decomposing some functions, finding functions f and g that compose together and give you another function, and look at an application of compositions of functions. All right, so decomposing functions is used quite a bit in calculus. And so what we're going to do is we're going to find the two functions f and g that if we compose them together, we get our function h. There are typically multiple correct answers to this. We are going to stick with one that is the most obvious. And so really when you're looking at these functions, you want to identify an inside function and an outside function. All right, our first example, we have h of x is equal to the quantity 2x plus 7 raised to the 6th power. Here, our inside function is going to be the one that's in the middle of our composition. So if we want to find these that compose together f of g, that means g is going to be in the middle. G is going to be our inside function there. And so one of the options that we can use for that is 2x plus 7. And then if we take out that 2x plus 7, what we have is our g raised to the 6th power. So our f of x function is going to be that. We're going to be taking our function and raising it, taking our value and raising it to the 6th power. So this is one option, and this is the one that we're going to be using when we get to calculus. Another option, just to show you how you could do this, you could write this as g of x is equal to just the 2x, and then your f of x would be, in that case, what we're plugging in, the 2x in this case, our g, plus 7 raised to the 6, which would be another option. But when it comes to the calculus and trying to find a derivative of this x plus 7 still poses a problem. We want to write it with just an x. And so there are multiple correct answers, but typically one of them kind of makes it simplifies both of those functions. All right, our next example, we have x squared plus 3 underneath the square root. And so again, we can make our g of x be that inside function, the x squared plus 3. And if we replace that with just an x, our outside function becomes the square root of x. All right, now let's look at an application. So the surface area in square meters of a hot air balloon can be written as S of r equals 4 pi r squared, where r is the radius in meters. If the radius is increasing with time in seconds according to the formula r of t equals 4/9 t cubed for t greater than or equal to 0, find the surface area as a function of time. All right, so to write this surface area as a function of time, what we're going to do is we are going to replace, just like in compositions of functions, we are going to replace this expression in terms of t. We're going to plug it in for the r in our surface area function. So S of t is going to be 4 pi, but instead of using that r, we're going to use our expression for r, which is 4/9 t cubed. And then remember that r is squared, so don't forget we need to square that. So if we simplify that, squaring everything inside the parentheses, 4/9 quantity squared is going to be 16 over 81. And then we'll have t cubed squared, which is a power raised to a power. So we're going to multiply those exponents, and we'll get t to the 6th. Just cleaning this up just a little bit, 4 pi times 16 is going to give us 64 pi over 81. And that's still multiplied by t to the 6th. So that is going to be our surface area, now using the variable time instead of the radius. And so if we want to find the formula, or use this formula to find the surface area after 3 seconds, all we're going to do is plug in t equal 3. So S of 3 is going to be 64 pi over 81 times 3 to the 6th, and 64 over 81 times 3 to the 6th gives us 576 times pi, or as a decimal approximation, we would have 1809.56, and the units on that are going to be the units of the surface area, which is square meters. All right, I'll see you guys next time.